Today we're going to review all the first four sections of Chapter 11. We know that a minor arc is less than 180 degrees, and we use two letters to name a minor arc. So the two minor arcs I see here, one would be CB, and another would be AB. The order of the letters in a minor arc doesn't matter, right? So you can just say CB, and I have to have a little arc symbol above it for this one, and then BA or AB for the minor arc. A semicircle is exactly 180 degrees, exactly 180 degrees. And a semicircle can have two or three letters, two or three. So if I want to name a semicircle here, I could say ABC, or I could even say AC. Major arc is more than 180 degrees, and you have to use three letters. And the main thing here with this question has to be two different major arcs. So here's one here, CAB, and then another major arc might be, let's see, ACB. It's always hard to get that second one. One main thing about naming arcs is never use the center letter, because arcs never go through the center of the circle. Never use the center letter. When we have central angles, they have their vertex at the center, right in the middle, and then the arc and the angle are the same. So we say central angles are the same. So here is 64, that means that the angle in there is also 64. Then for the arc measures, I remember things like, okay, the whole circle is 180, or FGH here is half the circle or the whole circle is 360, half the circle is 180 degrees. GH, I would do 180 minus 164, so it's 116, right? 116. And then that angle GEH would also be 116. This is a longer problem where it's got a lot of angles, so sometimes I like to write it right on the picture first, like 81 is going to match 81, 135, 135. Let's see, well, DE here is 81 degrees. FB, I just said, was 135 degrees. E to F to B is half the circle is 180. So if I just want this little piece, I'm going to subtract 180 minus 135. That's how I'm getting 45. That makes EOF also 45. BOC, let's see, BOC, that's a vertical angle. I didn't notice that at first, right? 45, 45. And so then if I want to do D to F to B, sometimes I like to circle in those major arcs, D towards F, and then ends at B. So that's like 180 plus 81 more. So what's that? 261 degrees. Next one, we're going to write a little equation, right? Again, central angles are the same. So what I notice here is that the 3x plus 2 is going to equal 122, right? The 3x plus 2 is going to equal 122, so 3x is 120, so x is 40. Here, angle 1 is going to be 30 degrees because I did 150 minus, subtracted from 180. So 5x minus 10 equals 30 degrees. 5x is 40, so x is 8. Central angles are the same. Inscribed angles are a little bit different because they have a vertex on the circle. So we say that the inscribed angle is 1/2 the intersected arc, or the intersected arc is double the inscribed angle. This is the hardest section in the chapter. So the 80 degrees gets cut in half here for the angle that's 40 degrees. And then for the rest of the arc is 360 minus 80, which would be 280 degrees. Next one is 30 degrees for the angle, so I'm going to double that for the arc. The arc is 60 degrees, and then if I subtract 360 minus 60, 300 degrees. When I have an equation, this is 25, so this is going to actually be double 25, or 50. So it's not 6x plus 8 equals 25, it's 6x plus 8 equals 50, or 6x equals 42, or x is 7. Here, the arc is given as 140, so the angle is half of that, or 70. So it's 10x minus 20 equals 70. 10x is 90, x is 9. This one is talking about a semicircle, so WV, well, there's a couple things going on. WV, I notice, is going to be double 42, because that was an inscribed angle, so that's going to be 84 degrees. If I subtract from 180, I'm going to get 196 for this one. So this piece here is 96. 96, doesn't want to write. There we go. Degrees. XZV. Oh yeah, that's a semicircle, isn't it? So that's 180, and that makes the other one 90, because this is inscribed in the semicircle. So since this was 180, I take half of 180, or 90. It's always more confusing when there's two things going on in the picture. Like here, I see an inscribed angle for the 70. 70 divided by 2 is 35. And then angle 2 is also inscribed in the 70. 70 divided by 2 is 35. For this one, let's see, angle inscribed in a semicircle, I'm reminding you the rule is 180. It's the same thing, right? So LPN is a semicircle, so that's 180. So then the angle inscribed is 180 divided by 2, or 90. Here I've got some inscribed angles again. So arc DC, well, let's see, I got 140 plus 98. So what's that? 238. 238 when I just added them up. And if I subtract it from 360, I'm going to get 122. So for that arc, 122. And now each angle's inscribed. So angle D is going to be half of 98, or 49. Angle C here is going to be half of 140, or 70. And then the last one here would be half of, half of 92, or half of 122 rather, which is 61. Oops, 61 degrees. Oops, 61. You get it, 61 degrees. Okay. Moving on, central and inscribed in the same picture. So the central is the same, so the central is 60. And then the inscribed is half, so the inscribed is 30. Central is the same, so 60, and the inscribed is half, or 30. Same thing again, the central is the same, so this angle's 82, where the inscribed is half, 41. Here they're giving me the 100 first, and that's central, so central's the same, 100, and then if I divide that by 2, 50. Same thing here, 110 is same 110, and then divide it by 2, 55 degrees.
How many videos do you have left to make?
Tangent and a radius form a 90-degree angle all the time. The two tangents, remember we said that ice cream cone rule, that they are equal, and that all radii of a circle, anytime you have a radius, they're always equal. So we're kind of through the hard part, and now we're on to like, oh, well, wouldn't that be 12? And wouldn't XP be 5? And isn't 12 plus 5 17? Ice cream cone rule for the next one, if it's 8 here, it's going to be 8 here. There's so much in this chapter where it's like, if it looks equal, it is equal. AB is 5, BC is 8, DE is 7, and then if we add all those up, what do we have? 12 and 13 is 25, and 25 and 15, 40. Again, if it looks equal, it is equal. 4x plus 7 equals 7x minus 8. So here 3x is 15, x is 5. Here 5x minus 4 equals 2x plus 2, so 3x is 6, so x is 2. Right angle where tangents and radiuses meet, so this is going to be using our favorite theorem, Pythagorean theorem. 144 and 225, and I believe that turns out to be 81, and the square root of 81 is 9. Here I've got radii of a circle here, so this AD is going to be 6 to match, which makes AC 10. And then again, it's a right triangle, so x squared plus 6 squared equals 10 squared. And this we've done a whole bunch of times, and every single time we do it, it always turns out to be 8. Last one here, 8 matches 8, 15 matches 15, and then I guess OR would have to be drawn in, and again, that's a right triangle. OR is the hypotenuse, C squared, And then this turns out to be 289, and the square root of which is, right, 17. Next we have common tangents. These touch the circle each at one point, so it's just a quick drawing, right? Common tangents, common tangents, common tangents. And you want to be, I mean, that wasn't the greatest I've ever done, but you don't want to be too sloppy about it. It helps me to draw the points first and then connect them, and sometimes there's no common tangents. Inscribe always means inside, and then circumscribed is outside. To inscribe a pentagon in the circle means like a five-sided shape inside, and we always want to make sure that the corners touch each time. Inscribing a circle in the hexagon would be the biggest circle you can draw, circumscribing a triangle, and then circumscribing a circle. So all the corners are always touching. Congruent chords mean congruent arcs, and if a diameter is perpendicular, then it bisects. So here I see those congruent segments, and then that means that all those arcs are congruent. JM, JK, KL, ML. Congruent chords here mean congruent arcs there. So again, it's like if it looks equal, it is equal to AC is equal to BC. Congruent angles make congruent chords, make congruent arcs, so BE and CD. And then here the congruent arcs, of course, are AC and BC. Perfect. Now we're getting back into some central angles here. So I see that 61 is going to match here, 61, since those are congruent, 61, 61, 61. EBA is like this whole arc from E to B to A. That's including that DB there. So that's that whole half a circle of 180. 61 and 61 is what? 122. So if I subtract 180 minus 122, what do I get? 58. So 58 for those two. Another one where they're equal, so the 65, of course, would match this 65 here. BD then, what's 65 and 65? 130. BCD is then the rest of the circle. 360 minus 130 would be 260. And then if that gets cut in half, that's 130 and 130. Similarly here, we got a 40 and a 40. That adds up to 80. Then the rest of the circle, 360 minus 80 is 280. And then that gets divided in half, 140, 140. Right to solve for x here, if it looks equal, it is equal. So the 3x plus 16 equals the 12x plus 7. So 9x is 9, so x is 1. 13 plus 4x equals 6x minus 5, so 2x is 18, so x is 9. I know this feels like this worksheet goes forever. Let's see. NF is 5 and CF is 2. It's not letting me write it there. 5 plus 2 gives me 7, so then EN is 7 also because that's a radius. Now in this one, if EF is 11, let's see, DF, well that would match it, right? So that would be 11, so then ED would be 11 plus 11 or 22. If ED is 106, that's just going to get cut in half, so 53 and 53 for those two. If HND is 118, that's going to match there, so that's going to be what, 62? Yeah, 62 for CD, so 62 for EC. If FN is 6 and ND is 10, got our old friend again, Pythagorean theorem. We've done that enough to know that that's going to be 8, right? 6, 8, 10. I'll still show the work. If I subtract 36 from both sides, I get 64. And then E to D would be 8 plus 8 or 16. Oh, finally, last one. ED is 48, so that makes EF 24. And then FEN is 26, so again, it's Pythagorean theorem. X squared plus 24 squared equals 26 squared. And this one we've done a bunch as well. It turns out to be 10. So if that's 10, CN is a radius, so it's going to match the 26, and 26 minus 10 is 16. Oh, phew. Yes, that's it.